Welcome back, trend busters, to my channel about economics, stocks, bonds, and estimation. If you are new here, make sure to hit that subscribe button and turn on notifications. That way, you won't miss any of our deep dives into the world of data and economics. And hey, if you haven't already, check out my last video where we explore prediction with linear regression. Today, we are taking things up a notch and digging into some practical, hands-on insights with repeated sampling. Next, we will cover nonlinear relationships on a future video. Alright, here's what you get out of today's video. By the end, you will know how to assess the variability in your regression coefficients, why that variability even matters, and how estimated using a simple method in R. It's not just a cool statistical trick, it's key for reliable predictions. Ever wonder why the slope in a linear regression has a standard error? Well, that's because it can actually vary depending on the sample you are looking at. Imagine you are in a grocery store and you are trying to predict how much people will spend based on their income. Every group you survey will likely give you a slightly different answer, right? This variation in your prediction, whether it is high or low, tells you a lot about how consistent or reliable your model is. Alright, let's walk to the code to calculate the average of beta 2 across multiple random subsamples. Let's go to R. Okay, so here the title is Assessing Regression Coefficients Through Repeated Sampling and Variance. Okay, remember that this is taken from or adapted from the Principles of Econometrics book by Colonescu. And yes, the idea is that we are going to create subsamples, and then we are going to recalculate beta 2. We are going to average the beta 2 that we are storing in a object, and we are going to observe how beta 2 varies across different subsamples and calculate the average to get the idea of its distribution and consistency. Okay, so let's go here in this R Markdown file to the R chunk. We know that is an R chunk because we have this quote brackets R notation. Right, remember that I already installed the library POE data, so it is not straightforward. So I suggest you to see my previous video to review how to open or install POE data. Yes. Is very different from install packages, the normal function to install packages. So I will hit here play. Yes, and everything is in there. In line 21 we create the number of observations. In line 24 we create C as a constant for the random on the number of subsamples that we are going to create. S is going to be, or the letter S, we are going to use it for the sample size of each subsample. And in sum B2 we are going to initialize a variable to store the sum of all beta 2 estimates. So we start this variable with 0, but we are going to carry on storing other numbers in there. I think the most difficult part of this code is to understand the loop. We haven't covered the loop yet in my videos. So to start a loop, we can start by for. We set a variable I, or can be any other variable. Yes, and this variable will take the values from 1 to C. Remember, C is something from It's a constant that has 50 subsamples. So this loop will finish once we arrive to c equal 20. So we will run 50 times everything that is inside of these brackets here. Okay, first of all, we set the seed and we do 3 times I. We do that because we want to create different subsamples to ensure randomness. Then we said here subsample is going to be this, so we use food, and then the function sample to create a different sample from the same food data set. So that creates a random sample using the same distribution of this data set. And then we say that it goes from 1 to n. Remember that we created n before. It is the number of observations. Yeah, so we are creating the same number of observations. The sample size or the size of this is S. S is in this case the desired sample size for each subsample. And we replace. Why we replace? Because this is a loop, so we will have to replace this object subsample every time that we run this loop. Yes, so that will be 50 times. So in this line, well, we draw a random subsample with replacement. Then we fit a linear regression model, as you can see here. Within this loop, we have fitting a regression subsample using the subsample, yes, between food expenditure and income. Remember that we use the function LM to fit a linear regression. Then we extract the beta 2 coefficient by using this notation. So these brackets means that we are looking into the lists of this mod2 object that, remember, it is storing the linear regression that we had here in line 38. Now we calculate and print the average beta 2 across all samples. So we create this variable beta 2. Oh, I forgot to mention that. Can you see that these brackets, we have brackets here? That means that we are going to create 50 times what is inside of these two brackets. Yes, once the number is 50, c equal 50, R will continue with the rest of the code, which is the average of all beta 2s that we have calculated and stored here in sum v2. We create this notation average underscore beta 2 to find the average of all beta 2 calculated from these subsamples. And you can see here that we print average beta 2 with digits equal to 3, which is rounded to 3 decimal places. Here this beta 2 is equal to 9.89, which compares with the calculation of the linear regression that was 10 point something. So very close anyway to the previous estimates using the data that has the model. Okay, so 9.80i represents the average of the 50 estimates of beta 2. And this gives us insight into the expected value of beta 2 and demonstrating that regression coefficients can vary depending on the sample that we choose. So for many applications, it's also very crucial to calculate the covariance of the regression coefficients, variance and covariance, and this information helps us to understand the uncertainty or a spread with each associated with each coefficient. Okay, so to obtain these estimates, we are going to use the function vcov bracket, yes, this function in R, which stores them in a matrix format. So here is how to extract the variance of beta 1 and the variance of beta 2 and the covariance between them. First of all, as you can see here, we run the model, yes, using the food data set, the original one, and then we use the function vcov, of model 1, the model created in line 59, and we use 1,1 to ask or to target that variance. We do exactly the same for beta 2. The only difference is that we use brackets 2,2 because in that place is stored the variance of beta 2 within mod 1. Then we can print var 2, and finally we extract and print the covariance between beta 1 and beta 2, and that is stored in the list 1,2. Yes, so that is why we have here within this parentheses or brackets 1,2. Okay, and finally the order in line 71 is to print the covariance beta 1, beta 2. So let's hit here the play button to see if the calculations. So we can check here that actually we have the results. Yes, and you can check here in the console that we also have the explanation line by line. Yes, so var of beta 1, the variance of beta 1 is 1,884, for beta 2 is 4.38, and for the covariance between beta 1 and beta 2 minus 85. What is the explanation of the results? The variance of beta 1 shows the variance of the intercept beta 1, indicating the spread or variability in beta 1 across samples. The variance of beta 2 shows the variance of the slope beta 2, reflecting its variability. And the covariance equal to minus 85 indicates the covariance between beta 1 and beta 2, which tell us about the directional relationship between the changes in beta 1 and beta 2. So this exercise illustrates how variances and covariances are essential for understanding the reliability of our regression estimates and how they relate to one another in a linear regression model. That's all for today. Thank you very much, and do not forget to subscribe.